So it's a great honor to be here and give a talk. And I indeed would like to talk about something more classical than for most of the discussions here. So I don't know much about emergent quantum mechanics. For my talk, it's sufficient to deal with Maxwell electromagnetism, which was formulated exactly 150 years ago. That's why we have the International Year of Light this year. But Maxwell electromagnetism is a very special theory because Maxwell equations are at the same time the relativistic wave equations for photons in the sense of first quantization. Therefore, what we have in classical electromagnetism should be consistent both with quantum mechanics and with relativity. And it's what I would like to show that it's not always trivial to make even the simplest properties of photons consistent between these three approaches: classical optics, quantum mechanics, and relativity. Okay, so the motivation of my work is the following. Let's start discussing the main properties of photon, which is momentum and spin, momentum and angular momentum. And for momentum, in classical optics, we can open any textbook, and it starts with the Poynting vector. So, which looks very simple, like cross product between electric and magnetic field. But at the same time, we can consider classical light as a number of quantum photons. And in quantum mechanics, momentum is naturally associated with the de Broglie momentum, which is proportional to the wave vector or to the minus I gradient operator. Or if we would like to measure momentum density locally, we can involve quantum weak measurement formalism and use canonical momentum operator and post-select in the coordinate state. But the problem that Poynting vector does not resemble these equations at all. And if we take another formalism, which is electromagnetic field theory, relativistic field theory, we can derive momentum density using field Lagrangian and Noether theorem for space-time. And then we derive this momentum density, which is electric field, this is vector potential and gradient operator, which is, again, looks very different from these two theories. Therefore, we have the same physical entity, light, or photons, or electromagnetic waves. And if we describe momentum in optics, quantum mechanics, or field theory, we have three different formalisms, and we don't see similarity. And as I will show you, this discrepancy between these theories is related to separation of spin and orbital degrees of freedom of light, to the fact that how we can describe angular momentum separated into orbital and spin part for photons. Okay, I'll skip some references. And I'll start from the most traditional approach to optics, which I call Poynting vector religion. So if we open Born and Wolf, we can read that in optics, the averaged Poynting vector is the chief quantity of interest. The magnitude of Poynting vector is a measure of light intensity, and its direction represents the direction of propagation of light. This is a very important statement. So we believe that photons move along the Poynting vector. And in Jackson or Landau-Lifshitz textbooks, we can read that Poynting vector is associated with the density of the momentum of light. This is another important statement. But OK, direction of propagation, momentum density, how do we measure this Poynting vector? How do we measure momentum? And even in Wikipedia, the answer is radiation pressure. We believe that radiation pressure exerted by an electromagnetic wave on some matter probe is given by the Poynting vector. And in fact, I would like to show you that all these three statements are incorrect in the general case. So these are the pictures from some old papers, how we perceive propagation of light. This is, for instance, a transverse cross-section of focused Gaussian beam, and this is diffraction of light on half-plane screen. So we plot streamlines of the Poynting vector, which show some vortices, some non-trivial trajectories, and we believe that light propagates along these trajectories. This gives us the intuition in optics. And this intuition indeed works well for a single plane wave, which is the most trivial solution of Maxwell equations. So if we have a single plane wave propagating along the z-axis, and we calculate the Poynting vector, it's directed also along the z-axis, it's independent of the polarization, and it's proportional to the k vector. And if we put a small probe here, it experiences radiation pressure force in the same direction. So that's why we think that Poynting vector is a good momentum of light. But this is true only for the most trivial solution of Maxwell equation. If we consider something more general, which we can call structured or inhomogeneous optical fields, some waves which have inhomogeneities in amplitude, the situation changes drastically. And we can see that Poynting vector represents a very controversial quantity. So I will list few problems, few main problems with this concept. First, if we calculate Poynting vector in an homogeneous optical field, we can find that it has an anomalous component which is orthogonal to the wave vector, orthogonal to the propagation of light. And this strange transverse component proportional to the helicity, which is degree of circular polarization, which is spin degree of freedom of light. So to illustrate this, I consider on the two simplest examples of inhomogeneous optical fields. The first one is a single evanescent wave. Evanescent wave is an optical analog of barrier tunneling in quantum mechanics. So we have total internal reflection of light at glass-air interface, and here is classically forbidden zone for photons. We have exponentially decaying solution. And if we calculate Poynting vector here, it's shown by green arrow. It has an anomalous transverse component, this purple component, which is proportional to the degree of circular polarization to the spin of the incident wave. And the same happens in this inhomogeneous interference field. If we interfere just two plane waves, two photons propagating with different k vectors, and we locally calculate the Poynting vector for this interference picture, again, you see it's not aligned with the plane of the propagation, and orthogonal components of the Poynting vector are proportional to spin degrees of freedom, to the helicity of light. Therefore, Poynting vector cannot be associated with the direction of propagation of photons. Okay, so what about radiation pressure? As the most natural probe for the radiation pressure, local probe, we can choose a dipole, small dipole nanoparticle, or an atom, the simplest atom interacting with inhomogeneous optical field. And the radiation pressure force for small dipole particle has been calculated a long time ago. It's a well-known expression in optical manipulations, for instance, derived by Ashkin and Gordon. So you see that it's proportional to some quadratic form of the wave electric field. But it's not the Poynting vector. In fact, nothing similar to Poynting vector. And therefore, radiation pressure is not proportional to Poynting vector and even directed in some other direction as compared to this Poynting momentum. Therefore, again, it doesn't work. And finally, we have some fundamental problem when describing angular momentum of light, angular momentum of photons. In the Poynting picture, the angular momentum of light is given just by R cross P, as in classical mechanics. This is, of course, angular momentum density. But this is total angular momentum, not spin. It's spin plus orbital angular momentum. And we don't have explicit equation for these parts separately. Therefore, we have to separate spin and orbital degrees of freedom of light by hand. And in this equation, angular momentum is not an independent degree of freedom locally. It's just proportional to the same Poynting momentum. And this is related to the famous paradox in electromagnetism called spin of a plane wave paradox. So let's consider again the simplest solution, plane wave with circular polarization. So we believe that it consists of photons carrying spin along the z-axis. But when we calculate the angular momentum density using the Poynting vector, it vanishes identically. So there is no angular momentum in a circular polarized plane wave. But experimentally, we can put a probe particle, and it will experience a torque from this field. The angular momentum can be transferred to atoms, so we can measure it, but it's absent in the Poynting vector picture. Okay, so here is a typical optical experiment made more than 10 years ago, measuring spin and orbital angular momentum of light. And this is a very important experiment. So what you can see here is a so-called Bessel vortex beam, transverse intensity distribution of such vortex beam, and we put a small probe particle here. And the particle shows orbital rotation proportional to the orbital angular momentum in this beam. And at the same time, it shows spinning rotation proportional to the degree of circular polarization, to the spin in this beam. So we clearly see different degrees of freedom, spin and orbital and optical fields. And these degrees of freedom are separately observable. So to summarize the point in picture, Poynting vector doesn't look similar to quantum de Broglie momentum of photons. It cannot be associated with the propagation direction of light locally. It's not responsible for the radiation pressure, and it does not describe spin and orbital angular momentum of photons. So we have problems in such a picture, and as an alternative approach, I would like to suggest to start from relativistic field theory. And in relativistic field theory, we don't trust Born and Wolf. We derive the momentum density from the very beginning, starting from the electromagnetic field Lagrangian. And using translational and rotational symmetries of space-time, we can apply Noether's theorem and derive relativistic energy momentum tensor and angular momentum tensors. So the picture schematically looks like this. We derive energy momentum tensor, relativistic, and corresponding components gives us the momentum density of light. R cross this momentum density gives us the orbital angular momentum, not the total one. And if we derive the relativistic angular momentum tensors, it explicitly contains additional term, which is spin tensor. So we can determine spin angular momentum density in this field. And this spin density is completely independent from the momentum density. So we have different degrees of freedom from the very beginning. So this is a very good picture. But the problem is that these quantities we derive in relativistic field theory are gauge dependent. They explicitly contain vector potential for electromagnetic wave. And therefore, from the very beginning of field theory, they were considered as unsatisfactory and physically meaningless. So field theory physicists tried to improve these quantities. And the crucial thing was made by Belenfante and Rosenfeld in 1940. They tried to improve momentum density by adding some additional virtual part to it, which we can call spin momentum. And this part does not contribute to the total momentum of light, but nevertheless, it changes the picture drastically. So instead of the canonical relativistic momentum density, we obtain Poynting vector, and instead of spin and orbital degrees of freedom, we have only the total angular momentum without an independent spin of photons. And having this picture from the very beginning, Poynting approach, for 20 years in our optical angular momentum community, we tried to separate spin and orbital degrees of freedom by hand. And this culminated in 2009 in Michael Berry's paper, where he suggested separation of Poynting vector into orbital and spin parts, like in this equation. So in fact, he did think the opposite to Belenfante symmetrization in the beginning of field theory. So instead of doing these tricks with Poynting vector approach, what we suggest to deal with relativistic field theory, momentum, and spin. But we need to improve the gauge dependence of these quantities. So we suggest just to fix the gauge. We take the Coulomb gauge for the vector potential, which is equivalent to taking its transverse part. And this makes quantities gauge invariant. But what is important, there is a fundamental conflict between gauge invariance, Lorentz covariance, and locality of such a vector potential. If we take transverse part of vector potential, it's gauge invariant, but it's not Lorentz covariant. And moreover, it's non-local in terms of electric and magnetic fields. And this conflict is inevitable in Maxwell electromagnetism. So this is the essence of Maxwell theory. But if we consider these quantities in more practical aspect. For instance, we are in optical laboratory. We deal with experiments with lasers. We can conclude that we don't need Lorentz covariance. Any optical measurement is not Lorentz covariant because when you have a probe, it singles out a particular reference frame where the probe is in rest. Moreover, if we deal with monochromatic laser fields, monochromatic photons, these properties also is preserved only in a single reference frame. And for monochromatic light, we have local transverse vector potential, which is just proportional to the electric field with omega -1 factor. Therefore, for monochromatic fields in laboratory reference frame, we can consider this transverse vector potential, which solves all these problems. So the picture of field theory picture of momentum and angular momentum looks like this. We have canonically derived quantities from Noether theorem, momentum and spin density. We have improvement, in quotation marks, by Bielenfante, resulting in Poynting momenta. We tried to separate here orbital and spin degrees of freedom by hand, but instead of this, we can just fix the gauge in this canonical picture. Okay, and this is dramatic difference. The difference is here, spin is independent degree of freedom. In this picture, we need to derive spin using some non-local integral relations. So I will show that this picture is much more preferable and much more consistent with what we see in the optical laboratories. Okay, so this is the beginning of new paradigm. We start from the relativistic momentum density given by this equation, and for monochromatic field, it's reduced to this simple equation in terms of electric wave field and frequency. And we have another relation for spin density, which is independent quantity. What is good about these two new quantities? First, they have very clear physical meaning. Namely, they represent just the expectation value of the canonical momentum and spin-1 operators of quantum mechanics if we take the corresponding wave function proportional to the electric field. Or in terms of quantum weak measurement, these are weak values of these operators with the post-selection in the coordinate state, because we measure them locally. The physical meaning is that local momentum density is proportional to the phase gradient in optical field, so this is color-coded phase, and so it's local wave vector in such field. And spin density measures the ellipticity of the local polarization. It's always orthogonal to local polarization ellipse, not only in plane wave, but in arbitrarily monochromatic field. And the magnitude is proportional to the ellipticity. So these are very natural quantities. And if we calculate the momentum density in a homogeneous optical field, it's fully consistent with our intuition. Even in evanescent wave or two-wave interference, canonical momentum density is always aligned with the k vector with the propagation of light. So there is no mysterious transverse component. Moreover, what is most important, the radiation pressure force on a dipole particle is exactly proportional to the canonical momentum density. And 30 years after this equation was derived, we understand its physical meaning. This is not just some strange combination of electric field. This is canonical relativistic momentum density. Furthermore, if we calculate optical torque on a small particle or on an atom, the optical torque is proportional to the canonical spin density. And therefore, this provides the most direct way to measure this quantity locally in optical fields. This immediately explains optical manipulation experiments. Particle orbits proportional to canonical momentum density, and particle spins proportional to local spin density. These are two independent degrees of freedom and two measurable quantities. And this well-known picture, which was discussed today several times, weak measurements of photon trajectories or Bohmian trajectories, it's again fully consistent with this canonical momentum density, because what is actually measured is weak value of the momentum with post-selection and coordinate, and it's exactly proportional to this canonical momentum density from the relativistic energy momentum tensor. So this was emphasized and discussed in several papers. And finally, the paradox of spin of a plane wave fully disappears in this picture, because even for circularly polarized plane wave, spin density is a well-defined quantity. It's non-zero, and it's consistent with optical torque and spin of photons. So everything is good, but maybe we have even better news, because this new picture allows not only to resolve old problems, it allows to predict something new about light and photons. For example, if we calculate spin density using this formalism for inhomogeneous optical field, we immediately discover new type of spin of light, new type of spin of photons. Consider, for instance, this single evanescent wave. It can be regarded like a plane wave with complex k vector. Kz component is the propagation direction, and this component, imaginary component, is the exponential decay direction. And if we look at this electric field of such a wave, this is a solution of Maxwell equations in free space. It looks very unusual. Even for linearly polarized evanescent wave, without any helicity, helicity is zero, electric field experiences such an interesting rotation in the propagation plane. It follows cycloidal trajectory. So even without helicity, inhomogeneous field has some rotations, and therefore should have some angular momentum. And indeed, if we calculate the local expectation value of the spin, we find non-zero spin in the transverse direction, spin which is orthogonal to the k vector of photons. This is something new, and spin which is independent of the helicity of photons. So this is something very counterintuitive in terms of quantum mechanics. But nevertheless, this is measurable. If we put a probe particle, it will experience torque, which is orthogonal to the radiation pressure force. Interestingly, recently we interpreted this transverse spin in terms of so-called quantum spin Hall effect, which is the existence of surface states with opposite transverse spin attached to the opposite propagation direction. This happens in optics, for instance, in plasmonics. When you have surface plasmon polaritons, which are surface electromagnetic states, they carry transverse spin, and change in spin, you can change the propagation direction. So this is very similar to topological insulators for electrons. And there were recently several experiments published on this, confirming this prediction. Okay. So as before, this is a generic property for any inhomogeneous optical field. If you have interference of two waves, locally, spin density has this transverse component, which is again independent of the helicity of the interfering waves. And this was recently measured in this PRL paper for focused Gaussian beam. Near the focal spot of this Gaussian beam, this group measured spin density, and spin density is non-zero. Here it's positive, here it's negative, transverse spin density. So we can interpret these measurements in line of quantum weak measurements again. So we measure local spin density, which means that we measure spin operator with the post-selection in coordinate state. We cannot achieve spin 100 for photon, as predicted in this famous paper. But what we can do, we can achieve local spin values which are orthogonal to the momentum of photon, which is also anomalous. Because if we measure integral spin values, strong value of spin, it's always aligned with the momentum. But weak value can be orthogonal to the momentum. Okay, and another prediction also related to weak measurement is the difference between the magnitude of the Poynting vector and magnitude of the canonical momentum, which we now use instead. So if we divide Poynting vector by the energy density or intensity of light, this provides the local group velocity, local propagation velocity of light. And for Poynting vector, it's always subluminal, always less than c. This is very easy to show in free space. But for canonical momentum, it's not restricted. There could be regions in interference field where where this quantity is superluminal. We have local superluminal propagation. It doesn't mean superluminal signal velocity, it's local group velocity. And it corresponds, in fact, again, to weak value of photon momentum, which can be locally higher than h bar k. Michael Berry called this super oscillation phenomena. And such situation, again, can be realized in evanescent wave, which have kz vector larger than k in free space, or near the optical vortices, so-called phase singularities of light, where you can have arbitrarily large phase gradient, even accompanied by a very small intensity. This was discussed in many papers by Michael Berry and also Mark Dennis. And we found a very interesting work from 1978. It's almost a work which has almost no references, but this is a remarkable experiment. It's an experiment with evanescent waves and momentum transfer to atoms. So these authors put atoms to evanescent optical wave, and they measured momentum transfer per one photon. And the momentum transfer per one photon was larger than h bar k. This is an example of anomalous weak value of the photon momentum. And they emphasize that this is consistent with the de Broglie picture, but is not consistent with the Poynting vector picture. And recently also Michael Berry and Steve Barnett calculated the same super weak momentum transfer near optical vortices. So you can put atom near the optical vortex core, and the momentum transfer per one photon will be anomalously large, actually not restricted by any limits apart from the atom size. Okay, so finally, the final remarks is what about this transverse momentum component, transverse Poynting vector component I mentioned in the very beginning? This is actually the Bliokh momentum, which he added to improve the canonical momentum. So this is spin momentum proportional to the helicity of light, and this is curl of spin density. And according to our prediction, this spin momentum should not interact with matter. And recently we performed some experiment with a molecular force microscopy group in Bristol, where we measured radiation pressure from evanescent field created from total internal reflection on a probe which was a cantilever, very sensitive dielectric cantilever. And due to this geometry, we were able to measure different components of the Poynting vector, longitudinal, which is canonical momentum, and transverse, which is Bliokh spin momentum. And what we found that the force, radiation pressure force from the transverse component is 2 orders of magnitude smaller than the usual radiation pressure. Therefore, we have 2 components of the same Poynting vector, and they interact with matter dramatically different. So the Poynting vector is not a single quantity, it's in fact an artificial combination of 2 components. Okay, so to conclude, my goal was to provide a picture of momentum and spin of light, of photons, which would be consistent between classical optics, relativistic field theory, and quantum mechanics. And to do this, we had to adopt the relativistic field theory picture and canonical momentum and spin density. And this resolves many problems in classical optics, because now optical forces, torques, and radiation pressure are associated with the fundamental field theory quantities. And we are now able to fully characterize spin and orbital degrees of freedom of light. And importantly, because this is related to local measurements in homogeneous optical field, all these results are naturally interpreted in terms of quantum weak measurement, because these are measurements with post-selection and coordinate space. Okay, thank you very much.